At this moment, an object from another star system, known as Atlostri, is passing through our solar system. Every few weeks, its brightness doubles, creating a green cloud with a diameter of 500,000 kilometers, heading towards Mars. Astronomers expected a flare, but instead, Atlostri is now shining 6 times brighter than anticipated, puzzling ground telescopes and sparking heated debates about the reasons for this phenomenon. This may be related to a hyperactive core, sunlight releasing alien ice, or something entirely different. The closest approach to Mars is expected in a few weeks, and Earth will soon be enveloped in solar brilliance, so scientists are rushing to uncover the truth. Before Atlaster disappears from sight, it is important to determine what causes this unprecedented phenomenon and what secrets are hidden in its glowing coma. At present, Atlaster is about 2 astronomical units from the Sun. This distance is twice that from Earth to our star, about 300 million kilometers. Its speed is impressive. It is currently moving at nearly 60 kilometers per second and continues to accelerate. By the end of October, as it approaches the Sun, its speed will reach nearly 68 kilometers per second, twice as fast as any planet in the solar system, and enough to travel from Earth to the Moon in just over an hour. In terms of brightness, Atlostri reached magnitude 12. At first glance, this number may seem insignificant, but in practice, it means the comet is impossible to see with the naked eye. Even experienced observers need at least a medium-sized telescope to discern it, and only at night. In fact, the difference between the 6th magnitude, the threshold for the human eye, and the 12th magnitude is about 250 times. Nevertheless, despite these difficulties, the visible brightness of the comet is increasing much faster than the models predicted. The coma, a cloud of gas and dust surrounding the nucleus, is rapidly expanding. Recent measurements show that its size is now several 100,000 kilometers, comparable to the diameter of Jupiter. This expansion not only creates a magnificent spectacle, but is also the main reason why telescopes are capturing more light from the comet than expected. In America, the coma reflects and scatters more sunlight, increasing the measured brightness of the object, even if the solid core remains hidden. All major observatories closely monitor these indicators. The Atlas team, which first spotted the object in early July, records every new position and brightness in real time, updating trajectory data and alerting the small planet center of any sudden changes. As they approached Mars and the perigee Nagrazon, these precise indicators, distance, speed, brightness, set the foundation for all future observations. In September, Atlostri exceeded all expectations, sharply increasing its brightness. The light curve that astronomers use to observe the brightness changes of objects over time unexpectedly deviated from the expected trajectory, causing a significant shock and sparking heated discussions among professionals and astronomy enthusiasts. At the center of this mystery lies the coma of a comet, a vast cloud of gas and dust surrounding its hidden core. As the coma grows larger, it begins to reflect and scatter more sunlight, making the object brighter in telescopes. By early October, the opportunity to observe Comet Atlas III from Earth is rapidly diminishing. Each evening, the comet descends lower into twilight, approaching the bright light of the sun. The angle between Atlas III and the sun, which astronomers call solar elongation, will decrease to 30 degrees by October 21st. At this level, even the most powerful telescopes on Earth will hardly be able to separate the faint light of the comet from the dazzling brightness of the sky. For most of the planet's inhabitants, the real window for observation has shrunk to just a few minutes right after sunset, when the comet begins to rise above the horizon before disappearing into the haze. Astronomy enthusiasts strive to make the last possible observations, sharing their failures and rare successes as twilight envelops the Earth. Some teams coordinating their efforts pass the observation duties from one shift to another, hoping to capture a few more frames before darkness falls. Professional observatories, equipped with stricter safety measures for their sensitive optics, have already begun to scale back their operations. The risk of equipment damage from pointing too close to the sun is becoming real, and few are willing to take that risk. It's not just about the lost images. As soon as Atlas III is beyond the sun, the data will be inaccessible. No direct measurements, no spectra, and no way to track changes in brightness or structure. This means that every remaining opportunity for observations until October 21st is of critical importance. The geometry of the solar system blocks access to the comet, which will disappear from view just as it enters its active phase. The only hope for continued observations lies in the spacecraft far from Earth. This burden now falls on the orbital probes circling Mars. For a brief moment, Mars becomes the only place from which to observe Atlas III. When ground telescopes lose the ability to observe due to sunlight, attention shifts to the fleet of orbital spacecraft around the red planet. Each mission brings new data. The European spacecraft Mars Express, with its high-resolution stereo camera and EGA spectrometer, is capable of taking pictures and obtaining chemical data from millions of kilometers away. The exo-orbital apparatus, located on Mars, is a trace geosorbot equipped with a spectrometer and a new AST. It is designed to detect faint traces of gases, water, carbon dioxide, and even exotic volatile substances in the comet's coma. NASA's MAVEN spacecraft, designed to study the upper layers of the Martian atmosphere, can adjust its ultraviolet spectrometer to detect gas and dust emissions, while its plasma instruments monitor the interaction of solar wind with this interstellar object. The Martian Reconnaissance Orbital Device, known for its high-resolution camera, can capture an image of a comet's core if conditions allow, although tracking a fast-moving comet is a complex task for any space device. The flight trajectory favors Mars. On October 3rd, LOST 3 will fly approximately 28 million kilometers from the planet. This is close enough for orbital spacecraft to attempt direct observations, but far enough to avoid dust protection protocols that previously hindered comet observations. A team of specialists spent weeks modeling and updating ephemeris to synchronize observation times. Each group of scientists strives to obtain their share of data: visible and infrared images for mapping the comet, ultraviolet spectra for measuring gas emissions, and plasma data for studying the interaction of the comet with the solar wind. They hope to see the core as a distinct point emerging from the expanding coma and determine the chemical composition of the substances released upon heating the comet. No mission can guarantee continuous observations. Plans depend on the limitations of the spacecraft's guidance, data bandwidth, and the unpredictability of the closest approach to the comet. However, even a few successful flybys can provide information unavailable from Earth. Direct measurements of dust, gas, and plasma will be conducted on a scale never before used for interstellar objects. The focus is now on Mars, and scientific teams are ready to seize this unique opportunity before Atlas III heads towards the Sun. The first thing that catches the eye in Atlas III is its bright green glow. Spectral analysts quickly determined the cause of this color by studying the comet's light for chemical traces. According to common opinion, confirmed by ultraviolet spectra obtained by both professional and amateur teams, the main culprit is diatomic carbon C2. When sunlight hits carbon-rich molecules in the coma, they transition to an excited state. Upon returning to a normal state, these molecules emit a bright green light, especially in the range of around 510 nanometers. This is a characteristic sign of active comets, but Atlas III stands out for its brightness even at a distance of 2 astronomical units. However, not everyone agrees with the details of this observation. Some research groups noted the possibility of the presence of carbon or cyanogen molecules, especially in the spectra obtained in early September. These substances can glow green or blue under the influence of sunlight's ultraviolet rays, and scientific publications have sparked debates about the methods of oscillation and background subtraction. Nevertheless, the most reliable data with the cleanest and broadest spectral coverage consistently shows that the emission of the C2 molecule predominates in the visible coma. The chemical composition is not just a visual effect. The high speed of the Atlas III comet means that solar radiation affects the fresh ice and dust with increased intensity, separating volatile molecules and mixing them with the coma. As a result, the green color not only indicates carbon, but also signals how quickly the surface of the comet changes as it approaches the Sun. More observers are noting strange changes in the appearance of Atlas III. A faint band directed towards the Sun represents the so-called anti-tail, which contradicts common notions of comets where dust is typically pushed away from the Sun by radiation pressure, forming a classic tail directed away. In the case of Atlas III, physical processes swap places. When a comet moves through the inner part of the solar system at extreme speed, like Atlas III is now, dust particles and ejecta from the core can move forward, especially if they are large or charged. These particles can form thin, sunward-directed structures, an anti-tail that is visible only from a certain angle. Plasma physicists emphasize that the rapid expansion of a comet's coma, combined with the high speed of the comet, creates a complex environment where electromagnetic forces compete with gravity. Charged particles of dust caught between the solar wind and the comet's tail can concentrate into narrow streams. These features directed toward the Sun are not permanent. They depend on the size of the particles, their charge, and the constantly changing direction of sunlight. The effect is enhanced by the unique geometry of the view at the end of September, when the orbit of Atlas III nearly aligns with the plane of its field layer. So far, reports of the Atlas III antitail remain preliminary. Astronomy enthusiasts and some professional groups noted possible signs of this phenomenon, but no peer-reviewed images or precise measurements have been published yet. This phenomenon is not new to comet science, but its appearance on an interstellar object at such high speeds is rare. Antitail adds another layer of intrigue to this unpredictable visitor, hinting at the complex physical processes occurring as Atlas III approaches the Sun. Each comet visiting our solar system has its unique characteristics, but Atlas III stands out even among rare guests. The first two interstellar objects, such as Mama and Borisov, set the tone for what astronomers expected. Mama was discovered in 2017, featuring a mysterious cigar-shaped object. It was an invisible comet without a tail, just a tumbling fragment that almost imperceptibly glided into the inner part of the solar system. 2 years later, Borisov arrived, a comet with distinctive features: a bright coma with a barely noticeable bluish tint, a classic tail, and a chemical composition dominated by water and organic compounds. Very similar to icy wanderers that orbit the Sun every few centuries. However, Atlas III does not fit into any of these categories. His comet is not only large but also unusually green due to a strong emission of diatomic carbon, which is not observed in most comets in the solar system. A burst of brightness that nearly exceeds the predicted values by 6 times has no parallels in the muted flight path of Mama or in the stable ascent of Borisov. While Borisov's tail, as expected, streams away from the Sun, Atlas III hints at the presence of a directed antitail towards the Sun, a characteristic feature of the rarest comets, but almost never seen in interstellar objects. Among the recent guests, such as SI 2025 R2 Swan and AI 2026 L1 who were active, Atlas III stands out remarkably. Its speed, chemical composition, and unpredictable behavior force astronomers to reconsider the boundaries between comets that originated in the solar system and those that appeared in distant planetary systems. Classifying such objects is not just about labeling. Every anomaly in Atlas's behavior opens a window into the physical processes that could shape small bodies throughout the galaxy. The stakes are high. Each new dimension could overturn decades of assumptions about what it means to be a comet and what stories these celestial wanderers can tell about the worlds they left behind. After passing perihelion, Atlas III will begin to dim, likely much faster than it brightened. Most models predict a sharp drop in brightness as the comet moves away from the Sun. Its coma will shrink and disperse into the darkness. For those hoping to see it, the conditions become increasingly harsh. A telescope with a diameter of at least 20 centimeters becomes the minimum requirement. Even then, only the most sensitive digital cameras can capture anything more than a faint spot. Visual observers will find it difficult to keep up with the swift retreat of the comet, while image overlay and careful background subtraction will be necessary to track any residual activity. The practical aspect of observing comets is now shifting to online panels within coordinated companies, networks of citizen science, some operating on Discord servers and others based on authoritative organizations, provide near real-time updates on the position, brightness, and morphology of the comet. These platforms collect raw data from amateur telescopes around the world, process it using universal algorithms, and publish light curves that anyone can follow. For many, this is the first time an interstellar object's fate is observed by amateurs almost in real time. But for science, this is just the beginning. Each new data point, each brightness curve, each spectrum, and each controversial discovery adds to the overall puzzle. How do interstellar comets behave as they pass through a solar system so different from their native places? What chemical composition, dust, and fading light can tell us about the building blocks from which planets across the galaxy were formed? Now the questions go beyond simple observations, inviting everyone with a telescope, laptop, or just curiosity to join in the search for answers as the Atlas moves into the darkness. Ground observations will end after October 21st due to the conjunction with Mars, and the flyby of Mars on October 3rd will be the last opportunity for detailed observations using several instruments. Detailed mission graphs of Martian orbital spacecraft have not been published, leaving gaps in our understanding and upcoming data. Unlike Oumuamua and I-26 L1, ATLO with 3 demonstrates cometary and atypical features. What will happen when it swings around the Sun? Its composition, decay rate, and structural behavior will form the basis for future research on interstellar visitors. For now, the true nature of the ATLO with 3 remains an open question of science, based on hard-to-obtain evidence and awaiting the next close encounter.